Good afternoon, everyone. I am Hatano from Tokyo Institute of Technology. So I am also the members of the cabinet members the committee, and so I am also forming the quantum strategy of Japan. And so quantum material and quantum sensing are the important strategy for Japan. And so with this, I'd like to talk about the current status and also the Q2B flagship diamond quantum sensor project led by the MEXT. So this is the title, and so this is the outline. So diamond quantum sensor. So I'd like to increase the number of the people who are interested in the diamond quantum sensors. So of course, application is important. So I'd like to have the people who are interested in application and also who have the surrounding technologies. Please contact me. And so I'd like to talk about also the research topics in QLIP today as applications. So the diamond quantum sensor is a growing stock. So I have data up until 2020, but it is also increasing, recently. So it is a 22% increase per year for the number of academic reports and academic papers, and so the quantum sensor becomes more accurate and precise, and so many people are working hard for the social implementation of the quantum sensors currently. So let me give you an overview of the quantum sensor. There are many qubits, but the spin qubit nitrogen vacancy center in diamond is that one of the carbon is replaced by the nitrogen, and so then as a result there is a vacancy. So because of this structure, it generates the great functionalities for diamond. Diamond is very close to the mid gap in terms of a conduction band. So this will not be affected by the external factors so much. So among the solid materials, so it has the longest spin coherence space. So it can perform in a wide range of temperatures, and the triplet ground states are the magnetic electric field and temperature and are sensitive to a magnetic electric field and temperature and strain. So that's why it can create great sensors, and also you can use the light with the green light, and it creates the red fluorescent, and with that intensity it senses the status. So initialization can be done with the green light, and then the readout can be done with the red fluorescent, and the control can be done by the microwave. So this is about the magnetic sensor. So this is a main benchmark, and squid and atomic have the high sensitivities, but the diamond of its sensitivity is still improving. And so we actually made the world best sensitivity last week, and we are preparing for the paper for that. And so the linearity is high because of this feature in the real world. Even with the noise environment, you can use this sensor. So you can create a pretty mobile sensor, and from atomic scale to a macro scale can be covered. So it's very scalable. So and it works with a large temperature range, and also it can be work under the strong magnetic field, and it's very robust. And also the vector imaging can be done as well. So it is it has a very important functionalities for sensing and also multimodalities, like a temperature and magnetic fields, like information and energies can be covered. So it has a multimodalities, and also then also miniaturization is being done. So on-chip integration is possible. So because of this, the small spatial resolution like protein and the cells and nerves and also monitorings for that is possible, and also it can be used for the automobile monitoring for EVs. So that's why people in the world are working on this area currently. So for the basic science, we have done a lot of studies for magnetic fields and electric fields and the temperature, local temperatures and the pressure and the rotation and spin. Nanoscale NMR technologies have been realized and investigated, and under the extreme environment, in the extreme environment like high pressure, high temperature, and high pressure, it has been tested already. So therefore, spatial physics and research is one of the application area. And so, as a science, this technology has been already investigated and studied. So currently, we are working on the application and the social implementation. So these are the core technologies, and quantum manipulation is important. So in order to cancel the noise, we have a quantum protocol, and which has a special feature for a quantum sensor. And analog and digital circuit technologies are also used, and the light technologies, optical technologies are used. So semiconductor technologies are the very important base. And so merging with hybriding with spintronics, we can generate a new functionality using a hybrid quantum system. And also quantum material is an important factor. So how do you create the NV centers? So there are two major ways to do that. First one is the using a high pressure, high temperature diamond synthesis, and so you inject the nitrogen in order to create the vacancy center, and also then you do the EV irradiation on the diamond to create the NV centers. And also, so we have the microwave plasma chemical vapor depositions to create the NV. So by using these technologies for the applications that I showed, it is scalable because we use a single NBC for the nanoscale application, and by creating the centered NBC in a shallow ensemble, or the you can do the bulk ensemble NBC. By doing that, you can target at the macro scale application, and also it is very flexible. So now I'd like to talk about the QLEAP, the research topics in the QLEAP. Let me explain the overview of a QLEAP. This is the QLEAP project by MEXT, and this is the one flagship project in the sensing. And so the Tokyo Tech University is a headquarters, and we have a prototype and sensing system layer and a prototype layers, application layer, and also basic science tech layer. So using this base, so we are trying to create a consortium and a research group. So if you are interested in, please contact me. And one target is to solve the social issues. and also to help achieving the carbon neutrality. So we are focusing on energy electronics such as the battery and the power electronics. So we'd like to improve the energy saving features of the battery and the power electronics. And especially, as you know, the EV market is expanding. So we'd like to apply this technologies to that market. So energy electronics and the power device and the power electronics and the battery multi-scale or multimodal sensings are our targets. One of the example is the EV battery monitoring. Here, as you know, it has a wide dynamic range for the battery capacity because the battery capacity is expanding. So you can monitor the current at a high resolution, and also it is important to monitor the temperature as well. So the resolution of the current is 1 ampere, but if it becomes a 10 milliampere, then you can expand the cruise mileage by 10%, which is the big benefit. So you can. So we developed a technology to sense the current and the temperature at the same time, and so we actually did. And so for the diamond sensor, we miniaturize it. So on the tip of the fibers, we put the sensing tips, and against the bus bar, we place the sensing tip top and upper and down, lower of the bus bar. So we also developed the technology to cancel the noise of the vehicle. So the one hertz, the temperature in 1 hertz and root hertz temperatures, and also the microfields can be measured. So it is very important for the application that it can measure both the temperature and a magnetic field, because we do that because of the changes is different in the magnetic field and temperature. So this is a battery discharge tester by the Yazaki Corp. So we are verifying the battery performance with this. So the current is from 1 milliampere to 1,000 ampere. So we actually change the temperature with such a dynamic range from 1 milliampere to 1,000 milliampere. So from 10 milliampere to 1,000 milliampere, we can monitor using this sensor. And if you show you the detail from the 1 milliampere to 1,000 milliampere, linearity is very wide, and also the current accuracy is under the 10 milliampere per hertz. Over a wide range, we can measure the temperature. So if we look at if we apply this to a double LTC, worldwide harmonized light vehicle cycle, we tested the charge rate of the battery. So with conventional sensors, the accuracy was 10%, but then we can actually monitor the remaining residual battery with the 0.11% accuracy. So it is the equivalent of the 14 millitons of the reduction effect So it's the about 0.2% of the emission in the transportation sector. And also you can reduce the capacity of the battery, so you can reduce the material such as lithium, like rare earth. And the second application is the monitoring to monitors the inside the power device. And in order to make a highly reliable highly performance device, you need to check the leakage currents and the temperature and electric field. You need to locally monitor the electric field, but we didn't have that method before, so we only simulated. So as a prototype type of measuring, so under the PN diode, we put the NV center, we created the NV center, and to monitor the local electric field. So then our measurement result is very close to the simulation result. And also in 2D, we did experiment to take the electric field in the 2D. So we were able to measures the up to the 2 milli MV per centimeter. So and another social implementation example is a healthcare area, especially cell and nerve and the cell need to be analyzed in a multi-scale. So there's one example that I'd like to show you. It's a very primitive example. It's a rat imaging of the rat's MCG. So it's the current magnetic field made by the current from the heart of the rats, and we measured that magnetic field. This is the microscopic pictures of the heart, and then this is the distribution of the magnetic field, and then we convert it to a current. And so current flow can be remodeled with the 1 milli scale of the resolution. So we're expecting the application or implementation to identify the arrhythmia location. So current conventional testing is very invasive and time-consuming and painful because you need to use the X-ray as well. But with this, with this magnetic sensor, the magnetic field sensor, you can solve that issue. And currently, we are measuring the brain using this. And also another application for cell is this is the fertilizer Excel. So quality of the fertilizer Excel has a relationship with the temperature inside. I mean, that is the expectation, academic expectation. There is no way to verify that before, but then we use nanoscale. We created the NBC on the tip of the nanoscale needle. And so this is supposed to be a video. So here, this is the diamond needle with the NB center. So we put that needle into the fertilizer Excel to measure the local distribution of the temperature. So you can measure the temperature inside the cell. So we came so far. As I said earlier, the quantum innovation strategies under the quantum innovation strategy, the up until 2039, that this solid-state quantum sensor roadmap has been already developed, and this quantum sensor hub is now the Tokyo Tech University. And based on this quantum innovation, we are going to have an international convention in November this year in Tokyo. So we will welcome your participation. So it's a summary. So diamond is an excellent host for spin bands to qubits. And also the spinning diamond has excellent properties. And our goal is to socially implement the electronics and healthcare. But if you have another idea, please contact me. And in QLIP, we have a multiple layers, and we also have an international collaboration. And we are going to need more wider collaboration. So we'd like to connect you, which concludes my presentation. Thank you very much.